Welcome everybody to my first session on the lecture about statistical energy analysis and hybrid methods. Statistical energy analysis, in short SEA, or hybrid method, hybrid FEM, SEA methods. The first session is about the introduction and the motivation. So why are we doing this? Why are we using SEA? And why are we using the combined version of hybrid FEM, SEA? So before we start and to get the full picture, we have to talk about the acoustic design process. So what are the goals of an acoustic design process? So first of all, we would like to get a high level of comfort in cars, trains, aircrafts and launchers. In this case, mainly for the payload, namely a satellite. We have to target to design low noise products for emission to the outside, to the environment, and to achieve all the legal limits that we have for specific noise source. But, and that's a very important thing in the daily business of a technical acoustician, we have to solve a target conflict all day. Target conflict between acoustics and many other disciplines like cost, weight, space and design. And the reason is that all the other disciplines, they have a, let's say, competing view in terms of what we need. Good acoustics needs heavy layers, needs space, needs some soft foam material somewhere that might burden. All those design decisions that we take are in competition with the other disciplines. So in the design process, we have to communicate with all the others and to discuss what is the best solution for the product as a compromise. Vibroacoustic isolation, what is that? There's a try for definition. So the vibroacoustic simulation is the discipline of modeling and predicting the acoustic waves and vibration of particular objects, systems or structures. Why do we perform simulation? That's the other big question and the next first step into the simulation that will be shown later in the lecture. Obviously, in the very early design phase, we don't have any test objects. So that means at that phase, the only choice that we have is to perform first guesses, estimations or predictions about the performance, acoustic performance of our product. Other disciplines are somehow doing the same. So statics, aerodynamics, crash, they do simulation in the early design and layout process. So first of all, we can use those models for our topics, but we also have to give answer to specific questions. And last but not, third item is the design and evaluation of noise control can be done by simulation. What is the impact of a new treatment to use more mass, more space? What is the impact of a new thickness of a sheet of metal or a new beating pattern? And this can be done by using simulation. And this time, last but not least, a better understanding of tests. Because a test cannot measure everything, and if we have a test performed at the same time we have the model available, we can get a much better insight into the phenomena that had happened in the test procedure. Finally, we perform simulation to improve the product, but also the design process itself. And a big but, especially in my experience, simulation will never replace all tests and or engineering judgment. There's often the statement of zero prototype development. This might be possible in specific disciplines. My personal opinion is that in vibroacoustics, with the complex systems that we have, we can tremendously increase the number of prototypes, but we will not be able to completely design or develop without any prototype. Okay, what is so special about vibroacoustic that there's even a word created? One specialty is that the dynamics of structures and fluids are different. So that means we have a completely different physics behind the wave phenomena in such structures. That leads to very different wave types, especially in structures. You have bending, you have torsion waves, you have in-plane waves, and so on. They have a completely different speed of sound. This leads to a different wavelength, which might vary over 5 orders of magnitude in the full audible frequency range. And if we consider all kind of components that we might have, glass, foam, soft stuff, and so on. When we try to print a figure or have a look at which is showing a kind of artificial response function. So we have the frequency here on the x-axis. We have any kind of response. It could be the pressure signal at the driver's ear related to a force excitation somewhere at the mount of an engine system. We have the low frequency area where we have this spiky, peaky behavior where we have several resonances and anti-resonances that we can find. In this frequency area, our wavelength is in the order magnitude of 1/10 of the system length, as it could be seen also here in the figure. We have the high frequency regime where the wavelength is very small compared to the system dimension, so as it is denoted here in this fuselage panel. And at the same time we have a mid-frequency area where we have kind of mixed area. So this is an area where we have a transition area where where the transition takes place from the modal behavior to the random behavior. This very low frequency leads to modes that are very near to each other, and this is why we can identify peaks, but they are overlapping here a little bit, leading at the end of the day to varying but smooth curve in the high frequency range. So what is the consequence of this? All those different regimes of the frequency range require different simulation methods. And this is one part of the lecture, because in the lecture here, wow, there's an ant. So in the lecture here, we will mainly lead with the yellow and with the red area. So to further argue on this, I will show you some examples. One well-known example is the test campaign from Bob Bernhardt, who took 98 trucks, which are supposed to be nominal vehicles, and he took it out of the assembly line. And he measured the force at the front axle and at the same time the pressure response at the driver's ear. I don't have the original figure, so this is what I've shown a reasonably recently developed car from my company, but in the original I think it was a Ford truck. First of all, he repeated this experiment at the same car several times, but different times of the day, different environmental conditions, temperature, and so on. And what we can see is that here in the low frequency area, the variation is quite low. But in the high frequency, we already get a variation of our response. So that means the response of the car changes during the different experiments. When he did the same experiment with 98 different cars, this leads to a much higher variation, also in the low frequency range, but to a very high variation in the high frequency range. So what is the consequence of this? So the consequence of this is that even a similar object, so it was supposed to be equal, leads to completely different or strongly varying responses, especially at the high frequency range. So whenever we perform a simulation, which of those 98 cars should we take? So that means that in the high frequency range, it doesn't make sense to predict the specific representation of this ensemble of cars. We should take an average and at the same time have a look at the variance of those results. A further experiment into this direction was the famous beer can experiment from Fahy. So he took a much simpler object than a truck. He just took empty beer cans. To get them empty, they had to be, I like this formulation, they had to be carefully opened and emptied. And this is not the original figure. Also, again, this is just a similar representation of this ensemble. But I think beer cans doesn't vary too much between the United Kingdom and Germany. First step in the experiment was to perform the same experiment again on one beer can. And here we already see that there is also this variation in the result, even though the test document is not changed. And that's an important point, and Fahy would like to emphasize on that. He said that this was definitely not due to the alcohol inside the can that has to be emptied or potentially drunken. Good. The same experiment was done with the remaining 23 of this famous ensemble, and here again we see the variation from the beer can results. So we see that we have a variation of around about 20 dB in all those different cans. So again, even the simple object has a strong variation around a certain mean value and around with a specific variation in the high frequency. So then coming to a simulation example, and this is an example which is more motivation on energy methods and not so much about realization, or let's say explanation. So this is just to show you what is the performance of statistical methods. So just consider two kind of models. So the first model, the setup is quite simple. Those are 3 plates. 1 millimeter thick steel plates, and they are arranged in this set configuration here. And they are excited by a force, and the force is arranged in such a way that unit power is introduced. So 1 watt is introduced here in this position where the arrow is denoted. This finite element model is supposed to be referenced. So the elements are small enough to give a good representation of the dynamic behavior of this. The degrees of freedom here is velocity or displacement. And it's a typical deterministic model representation of such a plate. On the right-hand side, you see the same configuration for an SEA, Statistical Energy Analysis, or SEA model. And we have here now 3 plates, and each plate is supposed to be a subsystem called SEA 1, 2, and 3. And here we have a power introduction at one specific point where we introduce the same power into the system. The degrees of freedom here in the simulation, that's energy and power introduced. But out of the energy, we can create the average velocity, which is calculated from the energy in the subsystem. And here we get the average velocity via averaging over the surface. And the squared average is presented as a result, averaged over the whole surface. So from the setup, the number of modes of those plates is somewhere in the same order of magnitude, so they don't change too much in size. And we apply finite element methods left-hand side and energy-based SEA methods on the right-hand side. Let's have a look at the first results on the first plate. For the first plate, we see that the agreement between the finite element reference solution is quite good. Starting from a specific frequency, we have some peak behavior here in the low frequency, but in the mid to high frequency range, the curves agree very, very well. This small deficiency here is not a deficiency of SEA, it's more deficiency of finite element, because in such high frequencies, so we talk about 4 kilohertz, the element size starts to be too big, so that the finite element mesh is not representing perfectly well the physics of the FE model. When we do the same, when we check the results of the second plate, we have a different situation. So here we just have really this peaky resonant behavior of the reference solution. But remember the figure with the low and mid and high frequency. For the high frequency, we got a relatively smooth shape of the reference result, which is quite well represented by the SEA result, if we try to find a kind of average or tendency here. This is even true for the third plate. Again, the low or mid frequency has nothing to do with the with the finite element solution, but for the high frequency above 1 kilohertz, we can say that SEA at least gives the global tendency in this frequency range. So another option is to say, as mentioned before, to formally really compare the FE and the SEA results, I should have performed an ensemble of different FE models that have slightly changed. I didn't have the time for that. But even without this ensemble averaging, the SEA provides quite satisfactory results here in this graph. Now let's come to another configuration. We take the same model, but now we replace the plate 2 by a plate that's 4 mm thick. So the steel is much stiffer now, and the number of modes is lower than in the plate 1 and plate 3. In this case, we have following effect. That means that those plates are supposed to be random. So random methods and SEA method should work quite well. But here, they will definitely fail because we still have the resonance or the resonant behavior. So, and this is just to give you motivation. What is the option for that and how can this be overcome? So for this, we take the similar models than before again, which, I mean, this is the FE reference, but you also have the SEA configuration of it. But in the third version, we replace the mid plate by a finite element model. And this is what we call a hybrid FEM SEA model, because we combining different methods. We combine an energy method with a deterministic method. So again, have a look at the results. More or less the same result as in the model before. So SEA and FEM are quite well agreeing. The reason is that this boundary does not impact the dynamic behavior of the full plate in total. When we check the second plate, we see that the result now is worse. So the SEA model does not represent well the FEM reference solution even in the high frequency. This changes when we take a hybrid model for the second plate. That means now we have an FEM coupled to an SEA plate. And we see that even in mid-frequency, the results agree quite well. So the FEM result is very similar to the FEM2 hybrid model, even though the excitation took place at an SEA subsystem. The situation is even worse now for the SEA model for the third plate. The third plate has the result has nothing to do with the reference solution. And the reason is, the obvious reason is that the coupling, the energy flow between subsystem 1 and subsystem 3 in a global SEA model, modeling the mid plate as SEA, is completely wrong. So the coupling is wrong. This is why we don't get the right result here in the third plate. When we switch to hybrid method, the situation changes again. We see that we had quite a nice, relatively good result in the mid-frequency, but for high frequencies, the agreement between the hybrid model and the reference solution is supposed to be very, very good again. So, as we have this effect very often in common models, so to say that we have some subsystems that are already as random and others are not, this is something that happens very often in the mid-frequency range. This is why hybrid FEM SEA is supposed to fill the so-called mid-frequency gap, where we have no methods available, and this is why I mentioned the yellow area in the example before. So the hybrid method helps to extend SEA to lower frequency by using specific subsystems that are there that are not yet random. Okay, so what have you learned? And we come to some conclusions. At wavelength, in the order of magnitude of system length, the system is called deterministic. We use deterministic numeric methods, for example, finite element or boundary element, or if the simple is simple enough, we can use alternative analytical methods. At wavelengths much smaller than system lengths, the system becomes dynamically complex, and they are called random. In this case, we use statistical energy analysis, and in short SEA, and this was created by line to calculate the ensemble average of system response. The failure of the deterministic models results is not due to lack of precision, and they follow really from the intrinsic random nature of the dynamically complex system. So again, please remember the example from the truck. Which of the truck is the right model, which is supposed to be the reference? So even if we use high frequency deterministic methods, we must average. Yeah? And this is something that is an important thing, because very often high frequency FEM results are compared to SEA results, and this is not correct. You have to compare the ensemble average with the SEA result. When systems are divided into subsystems, not all subsystems become random at the same frequency. And this is, as shown, addressed by the hybrid FEM-SEA method that was invented by Shorter and Langley a few decades ago. This lecture is exactly about both methods. It's about SEA and about hybrid FEM-SEA. Thus, deterministic methods is dealt with also, but only as far as possible or as required, but not in the very detail. So this is not a lecture about finite element methods. When we have a look at the global simulation strategy, there are a few things to say. If we have to model the full set of frequency, that means that in acoustics we have to use various methods to do so. And this is what is denoted in the figure. In the low frequency, we can definitely use deterministic methods like finite element or multi-body systems modeling. In the high frequency, we have to use SEA. If there are still some systems still deterministic, for instance, a stiff fuselage panel, we have to use a combination of both. And this is the hybrid FEM-SEA method. And if you have a look at those figures, this right rectangle, this is what this lecture and all the next videos will be about. The relevant figure that kind of determines if a system is random or if a system is deterministic is the so-called Helmholtz number. I've shown it before. That's a relationship, or that's a ratio between the length of the subsystem and the wavelength. The higher the Reynolds number is, the more we are in the random world. The examples that I will show you, especially the academic ones, they can all be followed because there's a Python toolbox called pyva. The wording comes from Python toolbox for Vibroacoustics, and there you can program, follow, try out all those examples that will be shown later in the lecture. What is the goal of this lecture? The goal is to enable you to create, understand, and evaluate SEA and hybrid FEM models. And that's a high goal because you will definitely need some experience with such things. You should be able to create a reliable subsystem configuration. So the decision how to subdivide your full car or your airplane in different subsystems is a very important decision in the modeling procedure. Very important, you should know and understand the limits of finite element methods in SEA. I mean, no method is perfect and they have specific limitations, and that's also very important that you know them. And last but not least, you should be able to model the abstraction. So to see, okay, do I need everything? Do I need every screw? Because you cannot never model everything, and you have to identify the important things in the model. To do so, I think it's worth giving a kind of time frame and global overview about the full session or lecture that we will have, and the concept of this lecture. Another thing is that the lecture is self-consistent. So hopefully you don't need any additional textbooks or whatever. Everything that is shown in the later session is presented and explained in the early versions. We start with a boring thing, a very boring thing, the harmonic oscillator. Why is that so important? Because there we see concepts of energy, of damping. We can understand resonances and modes, energy in dynamic systems, and this can be very well done based on the theory of the harmonic oscillator. We will extend such systems to complex systems of masses and springs. And at the end of the day, we will excite those systems by random signals. And that's an important thing to understand what happens to a dynamic system with many inputs if it is excited by random input. The next two steps are dedicated to waves. We start with the simple waves, which are the acoustic waves, because there's just one degree of freedom, that's the pressure. And there we deal with sources, radiation impedance, and so on. Why sources? Yeah, because that's the way how energy is introduced into our wave field. And we will see what is the relationship between the energy in the wave field and the pressure. But we'll also have a first check on reflection and transmission, because this is a first treatment of how different fluid regimes are coupled. From fluids we move to structures. Here we will create or derive all typical wave shapes or wave motion in structures. We will talk about plates and beams, or not beams, but just here in the lecture only plates. We will also define some point impedances, radiation impedances. And for the first time we will learn that the speed of sound is not always constant over frequency. There will be a frequency dependent, which leads to dispersion, and at the same time leads to a definition of group velocity, which is important because this is the velocity that defines the flow of energy in our wave field. When we have finished the wave story, we come to the system idea. The next two chapters dealing with fluid is with systems in general, and again we start with the simple systems, which are rooms or tubes or cavities. We will see how modes occur in such system, and we will derive some methods to calculate the system response and the radiation of sources into such systems, and also give a short overview how the FE model of such a fluid system is represented. Not going too much into detail, just to understand the meaning of the matrices. And next step, structure systems. Here we deal with beams, bars and plates, mainly plates in the lecture case. Again, we talk about modes, what is a good estimation of the modes, and we will have some simple representation of model system responses and how an FE model in the structure would look like. Again, what is the meaning of the element matrices in a finite element model? So when we have finished this wave and system topic, we come to random systems, which are the important theoretical construct for modeling SEA. We start with diffuse wave fields, because that's, I think, to my opinion, the best approach to SEA, to consider a random system by the construct of a diffuse wave field. Here we will see what is the energy intensity relationship, but also, and very important, what is the cross and autospectral density in such fields. And from all this, we will derive the excitation, and last but not least, an energy-based SEA subsystem modeling procedure. So we will first identify what is the global SEA model based on a simple energy and power flow approach. It's nice to have one subsystem, understood, but when you would like to create a full, let's say, a full model, you have to investigate the coupling of different systems. And here we go step by step to all the different options or opportunities of coupling. We start with the coupling of these FE systems. Then we will see what would happen if we couple an SEA to a finite element subsystem, or at the end of the day, what is the coupling between an SEA subsystem. When we mastering the last two items here, SEA and FEM, coupling of SEA, we automatically come to the hybrid FEM-SEA method. And from this hybrid approach, we will again derive the SEA modeling and SEA matrix, and see that from this, the SEA description follows automatically. What is the good thing, and this brings us to the next chapter, is this hybrid FEM-SEA method in combination with the diffuse field reciprocity is an excellent, strict and straightforward method to understand and to explain coupling loss factors, so how SEA subsystems are coupled. And this is the next chapter about. Here we go through all the different options of coupling subsystems, and especially SEA subsystems. We will deal with some point junctions, some area junctions. We will not deal so much with line junctions in the lecture. Here I would really say I would recommend to rely on the book, because I think this is hard to present in the lecture without not everyone falling asleep. And when we have developed the theoretical body of what we all need to create an SEA and hybrid model, we will start with the first examples. So we come to some simple SEA examples. The transmission loss test bench will be the first one. We will have talk about some box isolation examples and so on to understand the typical setup and simple setup of SEA. What are the quantities that we get? What are the critical items? How do we interpret power flow and so on? This is done the SEA example chapter. The hybrid topic, hybrid SEA examples. Here we rely on the most prominent one and very clear situation of hybrid. Why clear? Because we take a transmission loss facility where we have two reverberation chambers. The naming says that this is a random wave field, and a deterministic plate in the middle that is still modeled as an FE or deterministic subsystem, and we will see what is the result for the noise transmission in this configuration. But at the same time we will also compare it, like in the T-shape plate example, with the full SEA result to understand where are the limits, how far can we get with the frequency ranges. And last but definitely not least, I will come to some industrial examples. So here we learn a lot about where can we use SEA in car modeling, in subsystem modeling, aeroplane setups, also specific panels. This is a mix of full-scale modeling, but also some sub-details like sidewalls or back car designs to give you some practical example how SEA can be used. How hybrid SEA can be used, and what are the limits of all those methods. Good. So far for the time frame. Some convention and remarks should be shown. First of all, you have the convention here. Every complex number is bold italic. I like that because then it's really clarified that this is a complex number. Don't like this underscript line. This is available. So if you see something here in the lecture that's bold and complex, that's hopefully always a complex number. Bold denotes vectors, mainly geometry vectors. I use a positive time dependence. Just a hint from my side. If you're referring to a textbook, you should always try to learn in the very early phase if it's a textbook using positive or negative time convention. That helps a lot because all the formulas look slightly different if another convention is used. When I use curly brackets, that's a vector. If it's a rectangular bracket, it should be a matrix. You can find all the symbol conventions in the free symbol chapter of my book. So it's linked here. This is how it looks like. You see all symbols are mentioned and given, the conventions are given. And I think this is quite helpful if you are not totally sure what is the meaning of a specific symbol. Good. Coming back to the lecture again, you will find further information on our webpage. This is www.docpyva.com. And very important, especially for the book, you will see how you can order it. But, and it's a painful point from my side, you will find a very long and hopefully comprehensive errata list on that. Last but not least, an important thing is the Python toolbox. It should be quite well documented. As you can see here, you have a documentation page of it. You will find all the necessary information, how to install it. You can use it simply, install it via pip. We can also use Git if you would like to contribute to the project. But as you can see, you see lots of examples, the 2 rooms, all those examples that we will talk about in the lecture. They at some parts occur also here on the web page. So please feel free to test, check, and comment the solution. Good. Yeah. So far from my side, the only remaining part is there's a reference list. So those are the references that I'm using. I will show them also. I will put them in the extra information. You will find those references also on my webpage. And those are the second part. So these are all those references that are directly used in the lecture. All the others are add-on, but those 25 things are the things that are really created and used inside this topic and lecture. So that means we came to an end. Thank you very much for your attention. If you have any questions, remarks, and so on, feel free to contact me. And the best thing is to do so via my author page. And I'm looking forward to present all the other sessions then, step by step. Thank you so much, and see you again.